Okay guys, today we're going to finish up chapter 8. We're going to talk about electromagnetic waves. So there's this nice scene on this slide. It's got a rainbow and it's at the beach. So why show a picture like this when we're talking about electromagnetic waves? And here's the answer. Electromagnetic waves are light. So light that's reflected and refracted in this rainbow. The light that's allowing us to see this, this slide here. It's electromagnetic waves. And so that's what we're going to talk about today. We're going to learn how they work and be able to quantify them. So let's get started. Please have out your chapter 8 guided notes. There's quite a bit to write in today, so please stay with me as we go through these slides. So electromagnetic waves is given an abbreviation, EM waves. So electromagnetic. EM waves are all the different forms of light. Can we see all the different forms of light that there is?
No.
Can the human eye pick it all up? No. Is there light going through this room right now that we can't see? Sure. So that's going to be kind of we're going to talk a lot about that today. The human eye can only pick up a small portion of all of the different types of EM waves. So here's the cool thing about EM waves. No medium is required. So they can travel through even a vacuum or space. They don't need a medium. Like sound waves, they need to compress the air molecules, and there's rarefaction, there's compressions, and that's how we hear sound. Well, electromagnetic waves don't need a medium. So we can send them even through space, which makes them incredibly useful. So what are EM waves? Well, they're oscillating, which means they move back and forth, and they're electric and magnetic fields. That's where the name electromagnetic waves or EM waves comes from. It's an electric field and a magnetic field that are oscillating. Here's another important point about EM waves. EM waves travel how fast, guys? The speed of light. This makes them incredibly useful. We can send a text message from your phone to somebody on the other side of the world in literally no time. Okay, we can broadcast live events over the television. Basically, it's live no matter where you're at in the country or the world for that matter. They travel at the speed of light. That makes them incredibly useful because they can get even to the other side of the world very quickly. The speed of light is the fastest that anything can go. The speed of light is given the symbol lowercase c. You're going to see that a lot in this lesson and in the chapter. Lowercase c means the speed of light, and it's equal to 3 times 10 to the 8th meters per second. That is 300 million meters per second. It's the fastest anything can go. Nothing goes faster than the speed of light. Okay, so please remember that lowercase c is the symbol for the speed of light, and it's equal to 3 times 10 to the 8th meters per second. I will abbreviate it, guys, like this. C is equal to 3 e to the 8th. Please remember that. Okay, so what exactly are EM waves? Well, if you look at this slide up here, it shows us. So this wave that I'm kind of outlining here, this wave is a magnetic wave. It's a magnetic field. Now 90 degrees from that, there's another wave coming out. And this wave that I'm outlining now is an electric field. So that's why they're called EM waves. They're electromagnetic waves. They travel very fast at the speed of light, and they can go through even empty space. They do not need a medium to travel through. So let's review for a second a little bit about what we learned in chemistry. How is light formed, guys? Well, let's talk about the atom for a second. There's three particles that make up the atom. What are they? Proton, neutron, and electron. Which particle is responsible for light? Yeah, it says it right here. The electrons in the atoms. If you remember, when an atom gains energy, it can move those electrons, so it absorbs that energy, and it moves the electron to a higher energy level. Okay? Do the electrons like to be farther away from the nucleus, so in this higher energy level? Does it like to be there?
No.
No. And so what happens is that it quickly would like to return. But when it returns, so the reason that it went up is it absorbed energy. Can we destroy energy, guys? No. So when it's sitting right here, it doesn't like to be there, so it wants to come back down. But can it just destroy that much energy? No, you can't destroy this energy, so what happens? It gives that energy and it releases that energy in the form of what? In the form of light. And so a lot of times when you see light being emitted, it shows this wave, because light is a wave. But it's also a particle. When they're referring to light as a particle, they call it a photon. So a photon of light is released. That releases that energy and gives that energy back, and that electron comes back down to its ground state. So, what are all the colors that we can see? There's a good way to remember this, and you probably learned it in elementary school. How do we remember all the colors that we can see? Good. Roy G. Biv. What is the R for? Red, orange, yellow, green, blue, indigo, violet. So that's all the different colors that we can see. Yet, how come the light in this light bulb right here is releasing white light? White is a combination of all of these colors. So if you have electrons and they're releasing red, orange, yellow, green, blue, indigo, violet, all of those simultaneously, it's going to form white light. Okay? And so that's what's happening with these light bulbs. They're releasing all of these different wavelengths at the same time, and that's what produces white light. Or from the sun, same thing. And everyone is always curious about black. They say, well, what about black light? Actually, there's no such thing as black light. Black is the absence of light. And so when you see this slide in this portion right here, well, let's talk about a black shirt. What's happening if you have a black shirt on? What's happening?
Everything's not reflecting any light.
The white light that's coming out of the light bulb is coming into that black shirt. What's being reflected? Nothing. So that black shirt is absorbing all that light, and it's not reflecting anything. So black is the absence of light. Well, how do you have? I have a blue shirt on. Why does it look blue? Well, all of the white light coming from the light bulb is hitting it, but this shirt is absorbing what? Everything but blue. And so it's reflecting blue, and that's why you see this shirt as blue. Okay, so you got to kind of think about light. The light that you see is the reflected light off of an object. All right, real quickly, I wanted to talk about how do you get red and how would you get violet? Well, if this atom was to absorb just a little bit of energy, so there's an electron here and it moves up, that's just one energy level difference. It's going to come back down and release what color of light? Red. How come red? Because red is the least energetic color that we can see. Out of Roy G. Biv, this is the least energy. Now, what if you give the atom tons of energy? It comes clear up here to its highest energy level, and then when it comes back down, it's going to release what? Violet light. That means that violet, in terms of the colors that we can see, has the most what? Energy. Has the most energy. Okay, so hopefully you kind of remember how light is formed. So now let's move on and talk about the speed of these light waves, or EM waves. It says to find the speed of EM waves, use the following equation. Please write this down, okay? This equation right here is going to be very important today. So remember, the equation for the speed of a wave that we just got done talking about was v is equal to lambda times frequency, wavelength times frequency. Well, we don't use v anymore because how fast do EM waves travel? Speed of light. And so we're going to use c. c is the speed of light. Will you always know this value? Sure. And so you're going to either have to solve for wavelength or frequency, the one that they don't give you. But EM waves will always travel at the speed of light. And c is equal to 3 times 10 to the 8th meters per second. Okay. Now let's talk about the energy. How do you calculate the energy of waves? We're going to use this equation. You're supposed to write it down. Energy is equal to HF. So the energy of a light wave is equal to H times F. Now let's talk about what these variables mean. We know what F is. We've seen that before. F is the frequency of the wave. It's given in waves per second or hertz. Same thing. But here's a new variable, H. H is known as Planck's constant. It's named after the guy that came up with it. But it's kind of a long number. It's equal to 6.626 times 10 to the minus 34. Is this a very small number or a very large number, guys? Small. Very small. Times 10 to the minus 34, you would have to slide this decimal 34 times to the left. It's very small. Okay? And all it is a constant that you times the frequency by that will tell us the energy. So, before I go any farther, we have this equation. Energy of the light is equal to Planck's constant times frequency. That means as frequency goes up, as this wave becomes more frequent, so there's more waves per second, what happens to the energy of the wave? If frequency goes up, what happens to energy? It also goes up, because if you're timesing it by a larger number, the energy is going to be larger. So as the frequency goes up, so does, if I can spell does, so does energy go up. So what kind of relationship is that if frequency goes up and so does energy? That's a direct relationship here. Okay. Now the opposite should be true. What if frequency goes down? What's going to happen to energy? It's going to go down. Okay. So let me see if you've got this. I'm going to draw two waves. Here's the top wave, and here's the bottom wave. Top or bottom, which one has a higher frequency? The bottom wave has a higher frequency. There's many more waves here. It's more frequent, has a higher frequency. Now the important question. Which wave, top or bottom, has more energy? Bottom. The bottom wave has more energy. Okay, it's got a lot more energy. All right, so let's see if we've got that. So from this equation, E equals HF, you can see that as the frequency of the wave is increased, the energy is also increased, and vice versa. So it is a direct relationship. Energy and frequency are directly proportional. I think you had to write that in your notes, right? Did you have to write directly proportional? Yeah. Okay. So energy and frequency are direct. So if one goes up, the other one goes up. If one goes down, the other one goes down. Okay, but there's another way to find the energy of EM waves. What if it doesn't give you frequency, but it gives you wavelength? Okay, so what if it gives you the wavelength? Then we're going to use this equation. Energy of a light wave is equal to hc divided by lambda, which is its wavelength. Now, if you look at that equation, hopefully this is going to make sense. But what if the wavelength gets larger. So this wave now becomes longer. It's a lazy wave. The wavelength is longer. So the wavelength goes up. What's going to happen to the energy of that wave? It's going to go down. How come? Why does it go down if wavelength goes up? Yeah, we're dividing by a larger number, right? What happens if you divide by a larger number? Well, the answer gets smaller. Just like 10 divided by 10 and 10 divided by 1. Which one's going to give a larger number? Well, 10 divided by 1 is 10, and 10 divided by 10 is 1. So if this number gets larger on the bottom, that number, the answer gets smaller. So what kind of relationship is that, guys? That's an inverse relationship. As wavelength goes up, energy goes down. Now, the opposite should be true, right? If we do the vice versa of that, so let me erase these arrows. What if the wavelength is decreased? So now the waves are closer together. The wavelength is shorter. What's going to happen to energy? It's going to go up, because now you're dividing by a smaller number. You divide by a smaller number, the answer is larger. Let's see if you guys got this. I'm going to draw two waves again. Okay? The top wave, and then here's the bottom wave. Careful in how you answer this. Which wave has a longer wavelength?
Bottom.
The bottom, from crest to crest, is a lot longer. The wavelength is longer. Okay, but what wave, top or bottom, has more energy? Top one. Remember, it's inversely related, so as wavelength is decreased, it's way decreased here, the energy goes up. So, okay, from the equation, E equals hc over lambda, you can see that as the wave's wavelength is increased, its energy is decreased, and vice versa. So what that means is that energy and wavelength are inversely proportional. As one goes up, what happens to the other one? It goes down, and vice versa. Practice problem 23. I would like to have you guys answer this on your own. So if you're watching the video right now, there's three parts. There's A, B, and C. I want you to answer which one has the most energy for A, which color over here out of Roy G. Biv or there has the highest wavelength, and which color would have the highest frequency. So please take a second. I want three answers next to A, B, and C. So if you're watching the video, please hit pause and answer each one of those. Then hit play. Okay. Okay, so hopefully you have an answer. So we're looking at all these colors here. Which one has the most energy, guys? Violet. I agree. It has the highest frequency, right? Which wave has the highest wavelength? Red. Yeah, from crest to crest, that's the longest wave. So it's going to be red. Now, what did you guys put on C, the highest frequency? It's going to be violet. Since we see all the colors here in their waves, let me talk about this. A long time ago, DVDs, they used a red laser. Okay, but now you can buy DVDs that have what kind of a laser? Yeah, all of them use a blue laser now. How come? Yeah, the frequency here, look at the frequency of blue compared to red. It's a lot higher frequency, so the wavelength is shorter. How DVDs work, guys, is what they put little pits in the DVD, the disc itself, these little hills and valleys. And that's what the laser is reading, is little hills and valleys located in that disc. Well, can you get more information from a smaller wave, using a smaller wave, or a larger wave? Smaller, there's better resolution, there's more information that it can pick up because it's a smaller wave. And so they can fit a lot more information in a Blu-ray as compared to using an old red laser. Does that make sense? kind of how it works. All right, practice problem 24. This is an easy one. Let's see if you guys get it. A beam of light has the wavelength of 200 nanometers. Nm means nanometer, which is times 10 to the minus 9 meters. It says, how fast is it traveling? It's very easy. How fast does light travel? What's the symbol for speed of light?
C.
C. What is it equal to? 3 times 10 to the 8th. What? Meters per second. Guys, it's kind of a trick question. All light travels at the speed of light. That means all EM waves are going to travel at that same speed. Okay, let's go to the next one. And we did get it right. Number 25. It says a beam of light has a frequency of 5 times 10 to the 9th hertz. What is its wavelength? Okay, this one we're going to solve for wavelength. There's an equation that we just went over that has these variables in it. What is it? C is equal to what? Wavelength, lambda, times frequency. So please use that equation there. Plug in the information that you know. Do we know C?
Yep.
Sure. Do we know frequency?
Yep.
Yeah, so you're just going to solve for lambda. Please do that. If you're watching the video, please hit pause and try it. Okay, so hopefully at this point you have the answer, but here's how I would do a problem like this. Let's substitute in. What does C equal, guys? 3e to the 8th. It's the speed of light. Is equal to wavelength. Now we don't have the wavelength. That's what we're supposed to find. And we're going to times that by the frequency. It did tell us the frequency was 5 times 10 to the 9th hertz. So now we have an equation, one unknown. We can solve it. How do I get lambda by itself? Divide by 5e to the 9th. Over here it cancels out. And so lambda, or wavelength, is equal to 3 times 10 to the 8th divided by 5 times 10 to the 9th. Did you guys get that lambda, or wavelength, was equal to 0.06?
Yeah.
Now, what are my units going to be? Meters for wavelength. It's meters. Okay. That would be 6 centimeters, wouldn't it? If you switched it to centimeters. So that's about the wavelength of this light. Now, something I would like to point out. EM waves have very high frequency. Times 10 to the, or 5 times 10 to the 9th. That's a lot of waves per second, and that's going to be common with EM waves. You're going to see very high frequencies, these waves. Okay, and we did get it right. The wavelength was 0.06 meters. Okay, let's do one more like this. Practice problem number 26. This one is asking you to find the energy of one photon. Let's go back to that energy equation. Energy of light is equal to h times F. So please use that equation. Try to tell me and solve for E. Tell me what the energy of this photon would be. If you're watching the video, please hit pause and try this one on your own. Okay, let's see how you guys did. Energy is equal to h. This, what is that called? What is this variable called, guys? Planck's constant. It's equal to that long number. It's actually a very small number. 6.626 times 10 to the minus 34. Okay? And we're going to times that by its frequency. It did tell us the frequency was 5 times 10 to the 9th hertz. So all we have to do is times those together. And I'm getting this number, so the energy of this photon is going to be equal to 3.313 times 10 to the minus 24. Now it's an energy value. We just got done with the energy chapter. What are the units for energy? Joules. So we're going to put a J right here. Now, is that a very large number or is that a very small number? It's very small. Times 10 to the minus 24th. We would have to slide this decimal 24 times to the left. So it's going to be 0.0000. You know, it's a very small number. So, but that's just one photon. There is a lot of photons in the light array. So that's just one of the photons. Okay. And we did get it right there. Okay, I would like to finish this lesson by talking about something that's very important. The electromagnetic spectrum. Okay, so the electromagnetic spectrum, let's start with its definition. It is a range of all the possible frequencies. So it's all the possible frequencies of electromagnetic radiation, which again is just all the different forms of light. So it's all the different frequencies of light is what the electromagnetic spectrum includes. Electromagnetic radiation is all the different forms of EM waves, or light. So this spectrum just includes all of them. Can we see with our eyes all of the different forms of light? The human eye can only pick up a small portion of that spectrum. Electromagnetic radiation can be classified as, you're supposed to write all these down. There's radio waves. Yeah, AM or FM radio waves that your car radio picks up and turns those waves into sound. So you're telling me that radio waves are light? They are, but we just can't see them. Our eyes don't pick them up. Okay, so radio waves. Then we've got microwaves. Yeah, microwaves that you cook your food with. Is that light? It's just a different form of light. Our eyes can't see that though. There's infrared waves. This clicker or your TV remote uses infrared waves. Light that travels, obviously at the speed of light. We can't see that light with our eyes though. Okay, the part that we can see with our eyes is called the visible light spectrum, or the visible spectrum. Visible light waves. This would be all of Roy G. Bibb. Okay, now there's a part of the spectrum that has more energy or has a higher frequency than what we can see. Ultraviolet waves. Where do you see, where are ultraviolet waves? Where do they come from? The sun gives us UV rays. That's what gives you a sunburn. We can't see that spectrum of light there, but they are there. X-rays are a form of light. If you've ever gone to the dentist or the doctor and got an X-ray, they're just shooting light into your body. Now these light waves have a lot of energy. X-rays can go through soft tissue, but they're stopped by what? Bone. And so it produces a contrast there. The computer picks that up and produces a contrast of the soft tissue in your body compared to the bones. Even between soft tissues that are different, like tendons and muscles, they can give you an idea of what's happening inside of your body by using that. Okay, and then finally, the most energetic or the highest frequency waves are called gamma rays. These are given off with nuclear radiation. Gamma rays have a lot of energy. It's just a form of light. Now this light wave can go through our bodies and break DNA, so that's why it's very dangerous. But it can also even go through walls and concrete. It's very powerful. Okay, so this is the electromagnetic spectrum. We're starting here with radio waves, which are low energy. And then we kind of just increase the energy as we move down to gamma rays. So I've got a picture of the electromagnetic spectrum right here. Now this slide there's a lot going on. So I'm going to go slow and explain it. Please watch as we talk about this. So let's start with radio waves. What would you say? Now here's a picture of the waves and how they kind of look. What would you say about the wavelength of radio waves? The wavelength is very long. So we have long wavelength. What would that do to its frequency though? Yeah, it's very low frequency. These are long, lazy waves. And what about the energy? Low energy. So radio waves, low energy, low frequency, but long wavelengths. Then we go to microwaves. A little bit shorter with the wavelength, a little bit more frequent. That frequency goes up. A little bit more energy. Then we go to infrared. Let me stop at infrared for a second. Why infrared? Have you guys heard of infrared goggles? Okay, the military, they use infrared goggles and infrared light all of the time. How come? Because it gives them an advantage over the enemy. Most military operations are conducted when? At nighttime. For that reason, if you're wearing infrared goggles, you can see infrared light. But can the enemy? No. And so if you remember, when was the operation conducted when they got bin Laden? At nighttime. It's in the middle of the night. And that's why they can see with their infrared lights, and they can actually use infrared light sources to see things. Okay, but can the human eye pick it up? No. So let's go to the visible spectrum. Okay, again, it's just a small sliver of this whole electromagnetic spectrum. Roy G. Biv is right here. That's what the human eye can pick up. Then we go to more powerful waves. UV rays that are coming from the sun that give us sunburns. Obviously, they have more energy. They can burn us. X-rays have more energy. And then which has the most energy? Gamma rays. Okay, so now we're just going to zoom in on the visible spectrum for a second. So again, it's just this small sliver right here. Okay? We're not talking about gamma rays, X-rays, or UV, or any of these other low energy waves. Just the visible light. The visible spectrum is a portion of the electromagnetic spectrums that the humans can see, that our human eye can pick up. What's interesting is that can different animals pick up maybe portions in the infrared, yeah, or the ultraviolet? So different animals can see different things, but the human eye can pick up just about the visible spectrum right here. So these waves that our eyes can see are between the wavelengths of 400 nanometers to 700 nanometers. This would be violet, very short or higher frequency waves. This would be red, 700 nanometers. A nanometer is times 10 to the minus 9th meter. It's very small. To remember the visible light, we've gone over this. We just remember Roy G. Biv. That's all of the different forms of visible light. And there's the colors that it means. Okay. Practice problem number 7. Let's see if you guys got this. Which of the following EM waves has the longest wavelength? So think about wavelength, the longest one. So we're talking about the longest, laziest wave. In terms of energy, that would be the lowest energy. So take a second and see if you guys can do that one. Okay, so hopefully you guys did it, and hopefully you guys circled microwaves. They have the longest wavelength between all of these guys. So, very good. I've got a couple more questions on EM waves. Number 28. Now look, this is green light, blue light, red, orange, yellow. Which of the following waves has the most energy? Most energy. Okay, and hopefully, yeah, hopefully you're saying blue. Here's an easy way to remember the energy of the light waves. Roy G. Biv, isn't that already in order from least energy to the most energy? Okay, so just remember, red has the lowest energy and violet has the highest energy. It's already in order if you just remember Roy G. Biv. So the answer was blue light. Okay, so remember how light is formed. It's from the electron. It moves up to a higher energy level when it absorbs energy, but when it comes back down, then it releases light. So the atomic emission spectra, let's talk about that for just 1 second. Each element on the periodic table, now there's up to 118. Each one has different energy levels, and therefore these energy levels, which they produce light, each element has a light fingerprint. So when you give each element on the periodic table energy, it's going to absorb that energy and then release it in the form of light. But each element is going to release a little bit different wavelength or frequency of light. And so it's unique. Just like our fingerprints can be used to identify you because it's unique, we can use light to tell us what elements are in that substance that's releasing the light, couldn't we? Sure. And so here's what is called an atomic emission spectra. Now it's kind of complicated, but look up here for 1 second. Let's say we give an element some energy, and we have this instrument called the spectroscope, which is able to tell us the different frequencies of light. And let's say that instrument's telling us there's light here, there's a light band here, and there's light with this much energy being released. Well, what substance is that? What element is that substance made of? Hydrogen. Okay? Helium is kind of cool. Helium has a really dark yellow band right here, and it's the only one with a dark yellow band exactly right here. So if we had something that has helium in it, could we identify it based on the amount of light that it releases? Yeah. Or the color of the wavelengths of light that it releases? Sure. And so we can use this information to help us know what elements are in a substance. Okay, we can also use the Doppler effect with EM waves. When we talked about the Doppler effect, we talked about it mostly with sound waves. But it also works with EM waves. Now, here's how it works with EM waves. We either say that a substance can be blue shifted or red shifted. And here's what I mean by that. If we're comparing blue with red, which color has a higher frequency? Blue has higher frequency. Red has a lower frequency. So, if we look at a substance and its spectra, those bands of frequencies of light, are shifted toward the blue part of the spectrum. So it's moved a little bit closer to the blue. Is that object coming at us or going away from us? It's coming toward us. So if something experiences a blue shift, it's because it's coming at us. It shifts toward a higher frequency. Now, if something is going away from us, we're going to say that it's red shifted. It's shifted toward the red color, which is a lower frequency. So it's moving away from us. Let me see if I can explain that. If we look at a star, let's say through a telescope, we're looking at the star on the edge of our universe. And it gives off a atomic absorption spectrum. And we use that telescope, we put on a spectroscope on that telescope, and it tells us the wavelengths of lights that are absorbed. So these black lines are the light wavelength or frequency that is absorbed. And this is at rest. And let's say we look at that star at the edge of our universe, and it produces this one at the bottom. Notice these two lines right here that I'm moving my cursor over. Are they shifted toward the red part or toward the blue part of the spectrum? Red. They're shifted toward the red, so we say that's a red shift. Well, what is a red shift telling us? That they're moving away from us. And that's exactly how we know that stars on the edge of our universe are moving away from us. We see a red shift with the spectrum. That's one of the big evidences for the Big Bang. If things are moving away from us, the stars on the edge of the universe are moving away from us, well, then you ask why? Well, there must have been some event that put a net force on those stars that started them moving away from us, right? So there must have been some event happen, we call it the Big Bang, and that's why the stars on the edge of our universe are moving away. But not every star is moving away from us. What galaxy are we in, guys? The Milky Way galaxy. Do you know what the closest galaxy is to the Milky Way galaxy? Andromeda. Andromeda, if you did this and pointed your telescope at a star in the Andromeda galaxy, well, you wouldn't see this happening. What you would see is that these two lines right here are shifted toward which side of the spectrum? The blue spectrum. So we say it's a blue shift. Well, what does that mean about Andromeda and the stars in that galaxy? They're coming toward us. They're moving toward us. So blue shifted, higher frequency, they're coming at us. And in fact, a long time from now, Andromeda and the Milky Way galaxy are going to collide and then form a larger galaxy, a combination of us and Andromeda. So anyway, red shift or blue shift, okay? Please remember that. I've got a couple of practice problems to see if you understand that. Practice problem number 29. It says a star that is moving towards Earth will show an atomic emission spectra that is shifted toward A or B. Please take a second and answer that. Okay, so hopefully you have an answer. Again, it says it was shifted towards, actually we were moving towards Earth. Now if you're moving towards Earth, are you going to have a higher or lower frequency according to Doppler Effect? Higher frequency. So we're looking for a higher frequency. Which color has a higher frequency? Blue. So you're going to see a blue shift if it's coming at us. It's going to be blue shifted. Okay, last practice problem, guys. Practice problem number 30 says, a star that is moving away from Earth, will show an atomic emission spectra that is shifted towards A or B. Please try that right now and see if you can get this right. Okay, so hopefully you have an answer at this point, but if it's moving away from Earth, according to Doppler Effect, if something moves away, is it going to be higher or lower frequency? Lower frequency. What color has a lower frequency? Blue or red? Red. So this would be a red shift if it's moving away from us. Guys, that's the lesson today on electromagnetic waves. Couple of things to remember. Let me review. Do electromagnetic waves need a medium to travel through? No. So can we send signals from Earth to a satellite which is in space? Yes. And how fast would those light waves go? Speed of light. And that's exactly how text messaging or TV signals are sent so fast, is through electromagnetic waves. All right, before I stop the video, to give you some more practice with this, I've got a worksheet in the student workbook. It's titled Electromagnetic Spectrum Worksheet. So please go there right now and let's get that done. Again, it's called the Electromagnetic Spectrum worksheet. Let's get it done, and hopefully this video helped you.